We're talking about the limit theorems, and we'll look at an example now. Calculate the following limit. The limit as x approaches 2 of this polynomial, 3x squared plus 4x minus 2. And this is a really easy problem, but what I'm going to do is spell out each step and justify each step based on the limit theorems that we've looked at. So I want to calculate this limit, and I first note that this polynomial is 3 terms. And so this limit can distribute across these 3 terms. So I'll do that as my first step. This is going to equal the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of 4x minus the limit as x approaches 2 of 2. And I can do that because limits distribute over addition. And this minus here, this minus 2, is really the same thing as addition, because subtracting 2 is the same thing as adding negative 2. So I've just distributed the limit over addition. Then I can take this constant multiplier here out front, and this constant multiplier here out front, and that gives me this 3 times the limit as x approaches 2 of x squared plus 4 times the limit as x approaches 2 of x minus the limit as x approaches 2 of 2. So that last term hasn't changed, but I've brought those constant multipliers out, and I can do that based on the limit theorem that says the limit of a constant times a function is equal to the constant times the limit of the function. I did that in both of these terms. And then now I can deal with this x squared. X squared is really x times x. So I can think of that as 2 functions, each of them being the simple function x multiplied together. So I can say the limit of a product is equal to the product of the limits. So I can write 3 times the limit as x approaches 2 of x times the limit as x approaches 2 of x, which means I'll just square that, plus, and then these other 2 terms stay the same, 4 times the limit as x approaches 2 of x minus the limit as x approaches 2 of 2. And now I can evaluate this. This is 3 times, now here, the limit as x approaches 2 of x. Well, that just has to be 2, so this is 2 squared plus 4 times the limit as x approaches 2 of x. Well, that's 4 times 2 minus the limit as x approaches 2 of 2, which is just 2. And so that gives me 12 plus 8 minus 2 gives me 18 for my answer. Now the question is, do you really have to do that? Well, as a general rule, no, for especially just for a polynomial like this. But if you're told to evaluate the limit and justify your steps with the limit theorems, that's what you should write. And you might even want to put some notes out here in English over here on the right. Each step right here I could say the limit of a sum equals the sum of the limits. So if they were to ask a question, for example, on the AP exam, and on the AP exams it's very common for them to ask a question and say, justify your answer. And you can write, as you justify your answer, you should show your steps, and you can also write a written explanation in English for those steps. And so you could write something like this for each of these steps. In the second case, you would write a limit of a constant times a function equals the constant times the limit of a function. And over here for this step, we would say the limit of a product equals the product of the limits. Now you might notice in this case that this 18 we had here for an answer, that's the same thing we would get if we just plugged in an x value of 2 in for the variable right there. This would be 3 times 2 squared plus 4 times 2 minus 2, which is exactly what we had down here. 3 times 2 squared plus 4 times 2 minus 2. And that's always going to be the case for a polynomial. For any polynomial, the value of the limit at a particular x value is just the value of the polynomial at that x value. Let's write that fact. I'm going to write for any polynomial, we'll call it p of x, so some function p, the limit as x approaches a of p of x is equal to p of a, the value of the polynomial at an x value of a. Now that fact implies something significant for the continuity of a function. The value of the polynomial at x equals a is p, and the closer x is to a, the closer the value of the polynomial is to that value. Let me draw that real quick. Say here's some curve that's some polynomial function, and say here's some point a, some x value a, and then here's some y value p of a. What we're saying is that if you're at an x value of a, you're right there on the polynomial. Then you're at a y value of p of a. But not only that, the closer you get to a, the closer you get on this curve to this point, and the closer you're getting to the y value p of a. You can get as close as you want to a, and you're always getting closer and closer to that point, and always getting closer and closer to that y value. What that means is that there's nothing weird going on in the curve around this point. This is always a smooth, continuous curve right there. For a polynomial, there's never going to be a break or a hole. You can always get closer to a and end up getting closer to this y value. You're never going to run into an asymptote or any strange behavior around that point. Polynomials are always smooth, continuous functions. And this idea is known as the continuity property of polynomials. Now, as a result of that, limit problems with polynomials are typically pretty boring. They always end up with the same value here that you would get if you just plugged in the x value into the polynomial. But it's worth noting that polynomials are always continuous. And we basically arrive at that conclusion with an understanding of limits and the limit theorems. Okay, one more comment here before we move on. Reciprocals of 0 and infinity. The following ideas should also be fairly obvious to you based on the things that we've discussed so far. I'm going to write it like this. If f of x is equal to 1 over g of x, so function f and g are reciprocals, and the limit as x approaches some value, I'll say x approaches c, the limit as x approaches c of g of x is 0, then the limit as x approaches c of f of x is infinite. So what we're saying here is that f and g are reciprocals. If the value of function g gets really close to 0, then 1 over g right there is infinitely large. So the reciprocal of a 0 basically is infinity. And then we can also reverse that reasoning, and we can say if f of x is 1 over g of x, if f is 1 over g, and the limit as x approaches some value of g of x is infinity, so now our denominator is getting infinitely large, the limit of function g is infinity, then the limit of function f, which is the reciprocal of g, remember, if g is becoming infinitely large, then the limit of function f is infinitely small, or 0. So you can think of intuitively as the reciprocal of 0 as being infinity, and the reciprocal of infinity as being 0. We can't really take the reciprocal of 0 and the reciprocal of infinity, but we can express those concepts adequately with limit notation. We can imagine a value being infinitely close to 0, and then its reciprocal getting really, really huge. But this intuitive understanding of 0 and infinity and the reciprocals of those, that's the kind of intuitive understanding that Leibniz had when he developed these concepts.